is I'll first talk about the fundamental research and economic prosperity and the connection between the two, and then some examples of fundamental research in the physical sciences, physics, math, engineering, computer science, and the payoffs, what we get out of this fundamental research, and then a little bit on opportunities for participation in big science. So the first part, economic prosperity and the connection with fundamental research. So as you can see on, is this a laser? Yes, very good. As you can see here, this is a plot of GDP per capita in the USA over time. And the data come from reliable sources in the government. And what you can see is over a very long period of time, since the late 18th century, exponential growth in the GDP per capita. Here you have 1970, and it's difficult to see exponential growth on a short time scale, but you can see it on very long time scales. Exponential growth is interesting. We study exponential growth in the sciences. And what we know is that exponential growth means feedback. Something is feeding back and causing this kind of exponential growth. So the question is, what is feeding back? What is the cause of exponential growth in GDP per capita? The GDP is well defined as the gross domestic product of a country. Now, the world GDP is something like $74 trillion, and the US is about 25% of that total. Many other countries are growing economically as well, not just the US. You can see in this graph, this is the US, and you can see other countries. Some are growing more than the US per capita, most less, but this is on a very short time scale. How do we understand this curve, this relationship in feedback and exponential growth? How do we understand it? We have to look for correlations, and one of the correlations that we can look for perhaps is the GDP per capita as related to the amount of research and development, R&D, per capita. So that is an interesting thing to look at. And what you can see in the upper left is plotted GDP per capita, gross domestic product per person, and R&D per person spent in the countries. And the data is difficult to gather and has some uncertainties. However, what you can see is that people with low GDP per capita and low R&D per capita are correlated. People with high GDP per capita is correlated with high R&D per capita. So this is a very significant thing, and it's a very interesting clue as to what is the nature of the feedback mechanism. So, but you have to be careful when you study science and economics, when you think about correlations. That's not the same as causality. What causes something is not the same as something being correlated. Now, is the US richer, higher GDP per capita because it spends more on R&D? That's the question. It could be the US spends more on R&D because it has more money to spend. That's the question to answer. Or is there some other factor? What you can see in this plot, which is a very busy plot, but this comes from Batten magazine with information from the IMF and the CIA fact sheet and other collectors of information, is you can see the number of scientists per million people as a function of the ratio of GDP that goes into R&D. And you can see a clear correlation. So it is believed that this is really an important thing to look for, to understand how you make economic prosperity, and is R&D per GDP, R&D per capita, an important factor. So, does investment in fundamental research cause exponential growth per capita, or is it just correlated? And if it does cause it, how does it cause it? Why does it cause it? Many people believe that scientific investigations, fundamental research, which leads to an increased understanding of natural phenomena, also play a role in having a high GDP per capita, which means economic prosperity. Such research is characterized by perhaps not necessarily targeted to economic growth, but a byproduct, and motivating large numbers of young people to become knowledgeable in the sciences. People who, after completing their careers in education, in research, and completing their education, many go on to spend much of their career outside of science, contributing to economic prosperity in the private sector. These contributions allow for more support of science, and more support of science allows for more people to go into science, which allows for more contributions and more productivity. Perhaps this is the feedback mechanism that we've been searching for. Economists study this. What do they find? There was a famous economist named Robert Solow who received a Nobel Prize in economic sciences in 1987 who studied this. And he studied the theory of economic growth and the determinants to economic growth. And he developed a mathematical model. Now, this is an old model, started in the 1950s, and as you know, the world changes on 50-year timescales. And it has been superseded by more complex models, but the model still holds in general. What are the main factors of economic growth, he asks? Well, one set of factors that you would think are obvious: more labor, more capital, more land, more resources. These are all things that contribute to economic growth. But, and that's clear, but does it contribute to the exponential increase in economic growth per person? Well, having more land increases the GDP of a country, but not necessarily per person. And having more people have better jobs doesn't necessarily increase the GDP per person and capital and so on. This is unlikely to lead to the feedback mechanism. We're looking for a mechanism where productivity, something responsible for productivity, is generating more productivity. And the answer might be technological progress, and I think that it is the answer. Technology produces more wealth, which produces more technology, which produces more opportunities, and more technology, and more wealth. Exponential. They calculated that over 80%, perhaps 80% of the per capita growth in the US is due to technology allowing more efficient use of the resources that you need in order to have economic growth. The question after understanding the role of technology is the return on investment. This was studied. People wanted to know how good a return on investment is R&D, fundamental research and development. How good? What's the return? This was studied in many places. A classic study was in the UK, and I have a footnote here. The Economic Benefits of Publicly Funded Basic Research, a Critical Review. They found a direct return on investment due to increased competencies, techniques, instruments, networks, and the ability to solve complex problems. These investments increase useful knowledge, for the private sector to draw on, training skilled graduates who go to work in the private sector, making new instrumentation and methodologies, electron diffraction, photolithography, magnets, increasing connections between skilled people. Private sector research can be protected. So it's difficult for people in the private sector to share new technologies. Increased capacity to learn the kind of thinking that takes place in science and to apply it everywhere in the private sector and in the public sector as well. And creating new private sector entities, new corporations, new businesses. The survey from this study finds that these fields are important. Material sciences, computer sciences, mechanical engineering, chemical engineering, chemistry, physics, biology, mathematics, medical sciences, many others. And some of these fields return a tangible return on investment, arguably as much as 20% per year. And 20% per year means a doubling in 4 years. Now, not all fields will return 20%. If a field returns 5%, then they'll double in 14 years, which is a very good return on investment. Now, the question is, who should invest? This is a very interesting question. You would think the private sector benefits from economic growth and prosperity, so they should invest. But the private sector will usually only benefit, private sector investments are going to be geared towards that particular private sector business, not for the general private sector. Not that they won't, but they're there to make money, to have businesses flourish, and they will invest in what's in their best interest. They look for direct return on investment, and it's difficult in the private sector to justify huge numbers of fundamental research that have nothing to do with their business with a long lead time for return on investment. On the other hand, public sector investments can benefit the entire private sector and benefit society at the same time. For instance, indirect benefit of having talented and capable citizens. This plot here shows, as a function of time, the ratio of the amount of R&D per GDP in the USA. And you can see much structure in it. However, you can see that for many years, for 50 or 60 years, it's been averaging between 2 and 3%, something like that. Which means that, and here you see the very high, exponential increase in overall GDP. So as the overall GDP increases, the amount of R&D per GDP has stayed fairly flat in the US. And this is thought to be a real indicator and cause of this kind of exponential growth and prosperity in the US and in other countries as well. So we have seen why funding research and development, fundamental research, has economic benefits. The public sector investment generates new technology and technically skilled people. And the private sector can benefit and grow the economy. How do you promote this kind of thing? How do you do it? How do you get more people to want to go into science to be able to increase your GDP per capita and increase your prosperity? Let's answer this question. Let's start with human nature. The mysteries of the universe are never ending. And the more we learn, the more we know how mysterious it is. This is a real deep and wonderful thing about science. And the human desire and passion to know is universal and has been with all human beings since the beginning of time, when the first people looked up in the sky and asked, "What is that?" human existence and understanding the mysteries of the universe, they go together. Why should we care about these mysteries? Why should governments care if people pursue these passions? Well, for one thing, it enriches us intellectually and culturally. And it makes life worth living to have an enriched culture. Should governments consider pursuing investments in such things? And I believe the answer is yes, because studying science for the sake of unraveling these mysteries is a motivator for young people to go into science in the first place. And having people who understand science, as I discussed earlier, is a huge benefit to society and leads to prosperity for everybody. And as always, the most important thing is people. So let's talk about these motivators. Ignorance is a motivator. Ignorance is a motivator for addressing these mysteries of the universe because they are there and because it's our nature to want to know why things are the way they are. So here are some examples of some of the motivators, the big motivators. Many, many, many examples, and I have a few. Yeah.
Is it a video? Is it a video or just regular slide?
It's regular. Oh, there we go. Oh, thank you. So, one example of a motivator of a big mystery is the universe that we live in. What is the nature of this universe that we live in? Well, we learned in the 1920s and the 1930s that the universe was expanding. This was a big surprise. The makeup of the universe at that time, we thought, was atoms and stars, and atoms between the stars, mostly hydrogen and helium. A very sort of boring universe. And the rate of expansion, we believe, was slowing down due to gravitational attraction. Just like if you throw a ball in the air, it will rise, but it'll slow down. The question is, what is the ultimate fate of that ball? And people wanted to know, what's the ultimate fate of our universe? Well, it depends on the balance between the kinetic energy of the Big Bang and the gravitational attraction from the expansion. The universe could do one of three things. It could slow down and reverse so that our universe would get bigger and then it would come back to a microscopic universe, and somehow that would make the universe expand again, and we'd have this eternal oscillation in the universe over 30 billion, 50 billion year time period, a guess. That's one possibility. Another possibility is that it would just expand forever till it stops. Gravitational potential energy, kinetic energy, completely equal. And then a third possibility is that the universe would never slow down and would expand forever and become ultimately 100, 200 billion years from now empty, virtually empty. People wanted to understand this. It's a motivator. Do an experiment that measures how much is the universe slowing down. And if you could measure that accurately, then you could say something about the fate of the universe. How many people have ever managed to do anything that tells you the fate of the universe? Very, very difficult. They did this experiment, and they learned a huge surprise. Since the late 1990s, we have learned that the universe is 13.8 billion years old to a very high accuracy. And we've learned that is greater than 90 billion light years across. And we learned that atoms in stars and between the stars is a very small fraction of the total. Here are the atoms that we know from stars and from in between stars. 95% of the universe is a mystery. We did not know this 20 years ago, and we do now. And I can tell you in the US, this motivates many young people. They want to understand what is the 95% that makes up our universe. And they go into science. And they don't necessarily spend their whole career in science, and they understand that. But they go into it in the first place. It's a big motivator, an important one. Is there a technological economic advantage to such things? Yes. There are many examples of technological byproducts from exploring the mysteries in the physical sciences, because to explore these mysteries, you have to learn new things and build new things that you've never built before. And so people learn to be innovative, and they learn to build technology that they don't have. And they build it not because they want to help prosperity, but because they want to know the mysteries. This is so this is almost always how new technologies emerge. Almost always. Not always, but almost always. Consider the anecdote that describes why a government, a public sector, might want to invest in fundamental sciences. A man named Michael Faraday, a British scientist in the 1800s, was one of the fathers of electromagnetic theory, and along with Maxwell, really did 95% of the science of electromagnetics in the 1850s. And Michael Faraday had a lab, and the lab was at a university supported by the Queen, or the King and the Queen, Queen Victoria. And one day, the British Chancellor, William Gladstone, was visiting Michael Faraday's lab, and he saw all the experiments and all the things that they were doing. And he said, "Why are you doing this? Who cares? What does it matter? What is this, why are you doing this?" And Michael Faraday replied that he could not say definitely what this will come to, but someday you will tax it. And this is absolutely what has happened, because this is to be one of the big beginnings of technology, was understanding electromagnetic theory. So I have three general examples of the anticipated benefits of having skilled people who are well educated in the fundamental sciences and engineering, from direct science examples, the history of the internet as we know it and love, and the example of leadership. There's other examples, the example of big data, but that I'd have to say for another time. This is an example of how having people who are skilled in fundamental science can help society directly in the science, and become skilled people. The ear consists of the ear and the eardrum and a canal of fluid and nerve cells called the cochlea. And it's a long canal curled up in itself. And what happens is that fluid in there gets pushed by the eardrum. And due to the way this is built, the way this is configured, it will stimulate nerves along the cochlea. Now, some people who are deaf because their cochlea has no more nerve stimulation. It's lost its ability. So this is not that they don't have an eardrum, but they have no transducer to change from pressure, from sound, to electrical signals inside the cochlea. So what the physicists and the engineers did was they designed an implant, a long electrode that curls up around the cochlea. This electrode is connected externally to a sound processor outside the ear, that's taped attached to your head behind the ear. And that thing will hear, and it will send signals into the electrode and allow people to hear. And I know people who have these cochlear implants, and they're wonderful. They allow people who have no prayer of hearing otherwise to hear. This was not possible until a bunch of physicists and engineers got together and said, well, let's figure out how the ear works, and let's figure out if we can fix it. This is one example. Here's another example that's interesting, especially considering how Azerbaijan has recently procured its own PET scanner, one of the first in the regions. PET scanner is positron emission tomography, and it allows doctors to see inside the body what's going on with disease processes and things like that. It all starts with an equation written by Paul Dirac in Cambridge, England in 1928. This equation had nothing to do with medicine or economic prosperity. He just wanted to know, how do you reconcile the laws of quantum mechanics and the laws of relativity for particles? At the time, it was a mystery. From that equation came this surprising prediction that there are antiparticles in the world. And many people said, Dirac, you're crazy. But Dirac said, the equations are beautiful, and they're right. And Dirac was correct. Soon after, I think it was 1932, the positron was discovered. And the positron is the anti-electron. The Dirac equation led to PET scanners. A PET scanner is a device. You put your head in here, you attach a radioactive tracer to a glucose molecule, and you inject it into the blood. And the glucose molecule is metabolized by the body. So it travels around where the most metabolism is going to be. And you can take, okay, so this glucose molecule gets metabolized, and it has radioactive tracer on it. The radioactive tracer, when it decays into a positron. The positron goes out not very far and interacts with an electron from one of the atoms inside the body, right there, and emits two photons, very convoluted. The two photons can make it out of the body, like X-rays, and are detected by these detectors. The position and the timing information between the arrival of the two photons tells you where the two photons were in the head. You need precision timing. The computer reconstructs the image. This is a miracle, and it works. Now, what was needed to accomplish PET scanners? Well, knowledge of positrons, Dirac equation, and knowledge of the decay of the electron of the radioactive decay into positron, and knowledge that the positron and electron will annihilate into two photons, basic particle physics that we study. And how to attach radioisotopes to glucose molecules, basic biochemistry. And how to detect photons, technology, computers. And in the last 10 years, research into what are called solid-state photomultiplier tubes has allowed people to make PET scanners that are this small. Before that, they were huge devices with many photomultiplier tubes, which are about this big, way too big. The solid-state photomultiplier tube is a solid-state device made from silicon, sometimes germanium, that came out of the particle physics world and also the R&D coming out of the Defense Department to look for light emitted from missiles that take off from the Earth. Both contribute to the development of the solid-state silicon photomultiplier tube. These were developed for fundamental research, but they led to PET scanners. And here are pictures of the silicon photomultiplier tubes. These are arrays of counters and very small pixelated arrays. Here is a picture of what happens when you use a PET scanner in conjunction with a magnetic resonance imaging, another technology that came out of the Dirac equation because it depends on understanding the spin of a particle, the electron. And when you combine MRI with PET, you get these fantastic pictures. And here is a picture of a tumor that was seen by combining the images at one time, a combined PET and MRI scanner. Not possible to see this without that instrument. And this technology is saving lives, and it's a big business now, and it comes out of fundamental research. I'd like to spend a few minutes talking about a big product of fundamental research that has changed the world, the World Wide Web and the internet as you know it. The internet starts, the World Wide Web starts at CERN. CERN stands for the Center for European Research Nuclear. It's a large laboratory in Geneva, Switzerland. It's a multinational laboratory. It was founded in the 1940s by the Europeans out of the ashes of World War II and an understanding that we must work together to survive. The goals of CERN: probe the fundamental nature of matter and energy using beams. Technology? Not at all. Just science. Here is a picture of one of the accelerators that's used for these experiments, 27 kilometers in circumference, full of magnets. In the 1980s, CERN built that ring, the Large Electron Positron Accelerator ring, and a beam of electrons collided head-on with a beam of anti-electrons, and collisions began in 1989. The resulting collisions generates energy densities not seen since the first microsecond after the Big Bang. And the goal was to understand the Big Bang at that period of time. The radiation from the detectors was measured by very large particle physics detectors, and there were 4 of them at the time built at CERN. Each one was the largest detector of its kind ever built. And you can see the size of these detectors and the complication. And people were very excited to have the opportunity to build such detectors. Now, there's a catch. The data coming out of these detectors was huge. They were the very first big data challenges in the world. How do you analyze such data? But there was another problem that was also big, and that was how do you maintain the software and the documentation that people need? Because at the time, one computer might have a 50 megabyte hard drive, a 100 megabyte hard drive. Clearly not enough. Imagine you're limited to 100 megabyte hard drives. What to do? So in the 1980s, a man named Tim Berners-Lee from CERN put together a system that would allow access of the data without having to know which computer it's on. Because if you change the computer, you move the data around, you have to tell everybody. Doesn't scale, doesn't work. This was called the World Wide Web. It was a very primitive system just to allow you to say, I want some data, I have its name, I don't care where it is, you tell me. And so they put this system together, and this is the basis for the World Wide Web, which is an interface. But at the time, to use it, you had to type this long string into the computer. You had to type. No clicking. Type. Very clumsy. It was a curiosity at the time. And I remember getting an email from a friend at CERN and said, oh, you should try this. And I tried it and I said, it's hard to use, but it's nice. Okay, this was necessary but not sufficient. Meanwhile, in the US, the networks of computers, the research that developed networks of computers was taking off. It was started in the 1960s by the US Defense Department, who were anticipating protecting their defense establishments that are networked in such a way that if one of them was taken out by a bomb, the other ones would survive. And the universities got into this. And then at MIT, some of the computer scientists at MIT had a great idea. Let's figure out a way to use this new point-and-click technology that Apple had developed, use it generally, and come up with a scheme for having computers that you're sitting at talk to another computer and you don't really know too much about what goes on. It just works. That was called Project Athena. And it was to allow for campus-wide distributed access to computers. And they introduced the X Windows system. And it was not very easy to use, and it was not useful outside of MIT. But it was produced there. And people started to say, this is interesting. This is interesting, because it's powerful. The data networks are growing. People started playing with this, but it still didn't have the internet until the National Science Foundation funded what are called supercomputing centers. They had 6 or 7 of them. One of them was in Illinois, called the Center for Supercomputing Applications. And the leader of had a young man named Mark Anderson, and he said, he gave this guy something to do. He said, go take this interesting World Wide Web product that's very clumsy and merge it with an X Windows system so we can access it by just pointing and clicking. Maybe that would be interesting. He didn't know what it was going to lead to. This led to the internet, because now you put network computers, distributed access to the data, and point-and-click technology to get there, and it led to the internet. No one knew, but this came out of just fundamental research and people's wanting to exploit things and understand nature and understand computers. Here is the number of users on the internet, and it is getting close to everybody in the planet. This is a big thing that came out of fundamental research. The third thing I'd like to tell you about has to do with leadership. There are huge numbers of leaders throughout the world, especially in the US, who come out of the sciences. An example in the private sector is Elon Musk, who is the head of SpaceX and Tesla and the founder of PayPal. He has a dual degree in business and physics, and he has said, I'm not sure I would study business again if I could replay things. And about physics, he said, physics essentially evolved a framework of thinking that was very effective for coming to correct answers that are not obvious. He emphasized the first principle approach to problem solving. This is a key thing that you learn in the sciences, is reductionist thinking in problem solving. Richard Fairbank is the CEO and founder of Capital One, giant corporation. Fairbank, his father was William Fairbank, who was a physicist at Stanford and somebody who inspired me to go into physics when I was young. And Fairbank and I got to know each other, and he told me he gives his father credit for everything that's made him successful. Understanding science, understanding how to think. In the public sector, we have scientists who've played leading roles in all aspects of government. For instance, the current Secretary of Defense in the US, Ash Carter, has a PhD in particle physics theory. And then there are advisors who are who's who of American physicists. Wolfgang Panofsky, Burton Richter, Richard Garwin, Hans Bethe, John Wheeler. I mean, these are the best and the brightest people in science working in the public sector to try and help, to try and do some good. And I must say, academician Sagdayev is one of them. University presidents, many university presidents come from physics, math, chemistry, engineering. Here's just some example. At my university, huge numbers. University of Chicago, Berkeley, Stanford, and others from science backgrounds. UC San Diego, Queens College, UC Davis, and so on. People who can have successful science careers can often become the leaders of tomorrow. This is a very valuable byproduct of investment in fundamental research to allow these people to become the leaders, to make a huge difference in the world. Now I'd like to talk a little bit about big science opportunities. There are big trends in science. We now know that 95% of the universe is mysterious, and we know about multi-messenger science. Tremendous variety in both Earth-based and orbital-based telescopes and detectors. This huge variety of detectors can now be, they're all correlated, some mostly using GPS to know the time of the detection. It turns the Earth into a giant virtual multi-purpose instrument. And remember, you might say, well, what do we know about cosmic rays? Well, there's a few mysteries here and there. Why should we bother? Fundamental research inspires people to go into it. And making these detectors is a huge challenge technologically. People want to do it. And this is how the technology is developed. I've talked a little bit about CERN, a giant particle physics lab in Switzerland. It has a $1.2 billion budget. That's about 2 billion manat, roughly. 20 member states plus associate states. Science and education is a priority at CERN. The Large Hadron Collider is the flagship program with 4 large experiments, 2 of which, Atlas and Alice, already have participation in, from people from Azerbaijan. The strategic plan for CERN extends into 2030. So the efforts to upgrade detectors are beginning now. There's room at CERN for much more participation. Fermilab is the largest lab in the US. It has a $370 million budget. Science and education is also a priority. The flagship program is exploring the mysteries of neutrinos, where people want to know, what is the neutrino mass? And how can neutrinos change from one flavor to the other? How can that be? And what does that do? How does that explain matter, antimatter asymmetry? You know, we see matter, which is us. We see no evidence of antimatter in the universe. That's a mystery. Shouldn't be. But it is, because we're here. And Fermilab has significant dark energy and dark matter program. I'll tell you an interesting anecdote about Fermilab. It was built on time and on budget in the late 1960s. The director was a man named Robert Wilson, who had seen activity at Los Alamos during World War II to make the atomic bomb. And he went and spent his career building Fermilab. He was then asked to come to Congress a few years later because the congressman said, I want to know what we're getting for this. They're tough guys. They should be. They want to know, are we spending the money wisely? So they said to him, Professor, what are we getting for this? Are we getting new technologies from Fermilab? And he said, no, not really. And they said, well, are we getting new weapons from Fermilab? And he said, no, not really. And he said, is Fermilab making the country, is it contributing to the country's defense? Is it making us safer? And he said, no. But Fermilab is like, the science at Fermilab is like literature and poetry. It makes the country more worth defending. And they bought that argument. Fermilab has a huge program, and it's multinational, international program. And Fermilab, many opportunities for people from all over the world. IceCube is another opportunity. It's a neutrino telescope at the South Pole, funded by the National Science Foundation mostly. 12 countries have people participating. The goal is to establish neutrino astronomy, to detect neutrinos. Neutrinos can travel through a light year of iron without interacting. It's a mystery of high-energy neutrinos is how are they made? We don't understand how nature could make such high-energy neutrinos. Where are they from and what do they tell us? It opens up a new window to observe the universe. Neutrinos from supernovas will tell us about mass of neutrinos. And this is a fantastic detector consisting of strings of detectors in a square kilometer under the ice in the Antarctic. Here's one of the detectors, and here's what looking down into the ice. Fantastic experiment. Here's a picture of the Eiffel Tower. You can see the scale of this science here. Big science. Multi-messenger astrophysics I already spoke about. The universe is opaque to 1/5 of the electromagnetic spectrum. People want to know. They need to measure all over the place to see particles at different energies. And the last one I'll talk about is a smaller experiment called HAWK. It stands for High Altitude Water Cherenkov. It's an experiment 4,000 meters up in the Sierra Negro Mountains in Mexico. Very low budget, 24-hour coverage of the sky. They can see anything that happens. And high sensitivity. They have seen 40 new sources in the last year. And here is a picture of the experiment, and here is a simulation of a cosmic ray that showers and is detected by the experiment. And they've already seen 40 new sources from last year. It's a magnificent experiment that has many opportunities for new collaborators. So, investment in fundamental science is definitely correlated with future economic prosperity. The investment is in human capital and education, and an investment in knowledge pays the best dividend, or so says Benjamin Franklin, who was a famous American patriot and one of the discoverers that lightning was the same thing as electricity. In Azerbaijan, the economy is extremely impressive. Changes made in the last 15 to 20 years have been very effective. Inflation is under control, credit is extended, economic expansion. The UN ranks Azerbaijan 67 in the world in nominal GDP, roughly. Continued investment along the same lines will bear fruit, but doubling the GDP will only bring you to 57, just behind Kuwait. If the goal is to make a big boost and really increase it, the possible new added path would be increased investment in the fundamental research in sciences. Physics, math, chemistry, engineering, biology, anything. Anything that attracts students, people who want to know, get into science. Take advantage of the world projects in physics, astronomy, and etc. So, investing takes patience. You start with investment in people and education. You take a bottle and you put a pear stalk in it. And then you have patience. And pretty soon you have something great. Thank you very much.